The really great turnout. There was a lot of people at the poster session. So today we're celebrating the 75th anniversary of the Turing Test, or as some people know, the imitation game. It's my pleasure to be able to introduce the speaker, but first I'd like to thank our funders. We had the wonderful Fig Jam Indigenous Catering at the poster session funded by the School of Mathematics and Physics. And then we also had some funding from the Faculty of Science to help people print those posters. And we have a reception at Patina that is sponsored by the Center for Biodiversity and Conservation Science. So it's great to see support from all those different groups at UQ. So now it's my pleasure to introduce Professor Benjamin Burton at mathematics here at UQ, where he teaches supercomputers how to untangle knots. His academic career has spanned geometry, cryptography, finance, computer science, and he just finished serving as president of the International Olympiad in Informatics. He's a prominent figure in LGBTQIA+ inclusion in STEM and mathematics, and he's a wonderful speaker. But where I first met Ben was not in academia, actually. I met him at a running group, a queer running group in Brisbane when I first moved here, almost 10 years ago. And he's not only is he more brilliant than I am, he is also faster than I am. All right, so take the floor.
Thank you. And by the way, that same running group, there's a pack of them right there, so shout out to Brisbane Frontrunners. It's wonderful to be here. It's wonderful to have this event. This is, we should do this every year, Matt. No, this is great, and it's particularly wonderful to see so many people here who I've taught with, and there's a few who I've been taught by. Yeah, this is superb. But anyway, let me get into it. So we are here for the, well, technically for the anniversary of the Turing Test, sort of an excuse to do some big queer mathematics. I will get to the Turing Test later on, I promise. But in the meantime, I want to start with queer mathematics. And so we had a family function on the weekend. It was my father's birthday, and at some point we were chatting, and I mentioned that I was giving this talk on, I said, I'm talking about gay mathematics. And my uncle looked at me and said, what's gay mathematics? And I think he expected an answer, but it's a good question, right? So let's start with what is queer mathematics. The Turing Test, if you haven't heard of the Turing Test, you will by the end of the talk. The Turing Test was a test that Turing cooked up in 1950 to try and understand what it meant to be artificial intelligence. And they certainly had no such thing as artificial intelligence in the 1950s. They barely had computers. But it seems a good place to start. So we have artificial intelligence. This phone claims to have artificial intelligence. So I asked it, what is queer mathematics? Unfortunately, the first answer it gave me was this. So it did need a human as input. So I just put a picture of myself. And that's, so maybe my presence is enough to make it queer. I'm not sure. Maybe it's just the overly tight polo shirt, which I have a few too many of. So I thought this is no good. So I thought I'll be more explicit. So I asked for gay mathematics. Maybe that'll give it a better prompt. So it came up with this. Cute, right? Came up with this, which is a little bit adorable, but a little bit meaningless. Yeah, purple numbers. Who can? Then it started to go a bit off the rails. And then it came up with, now this is the one that I want on my laptop. I need this on a sticker, right? Anyway, but okay, so none of this is what is queer mathematics. Of course, what is queer mathematics is just mathematics, right? But somehow what we're celebrating here is mathematics that is done by LGBTQIA+ mathematicians and scientists and so forth. And so in that sense, I will be talking a lot about Alan Turing. So Alan Turing, I will come back to this probably more than once in this talk. I think many scientists have like an academic hero, a scientific hero, someone who more than anyone else they look up to, identify with, use their legacy of work. And for me, that is Alan Turing. And it's for many reasons, and it's particularly nice to be able to talk about Turing for this reason. But some of the reasons are scientific. A lot of what he's done feeds, after 75 years of work by many, many people, into a lot of what I do nowadays for my own research in untangling knots with supercomputers. I think there are many people in this audience, a lot of whom Turing's work feeds into what they do nowadays. Turing is, of course, also a big queer icon, right? From long ago, back when it was not remotely as safe as it was now, and I'll be talking about that as well a little bit later. But yeah, so I think the plan today is to talk through some of the big things that Turing's short academic life hit upon while he was active. And this is maybe a teaser tour. So the picture down the bottom here, this is an abstract notion of a computer that Turing cooked up in the 1930s. This is before we had computers. But Turing gave us the theoretical basis of what it even meant to be computation. And this is something that we still use today. I was teaching it to my, well, a substitute was teaching it to my quantum computing class 2 weeks ago. I was flitting off overseas somewhere, but we use it nowadays, right? People write theorems about these things nowadays in 2025. The thing up the top is the one that you may more likely have heard about, and this is the Enigma from World War II. So Turing there were many people involved in breaking the German ciphers during World War II, but one of the most famous is the work that was happening at Bletchley Park in Britain, and this is where they were basically building something that was a forerunner to a computer to crack Enigma keys, so they could read naval messages and somehow stop the German Navy from sinking all the ships in the Atlantic. And so this is something that Turing played a massive role in, and I'll be talking about that a little bit later on as well. The other thing I will say is, and probably my students who are here will already know this, I'm totally happy to be taken on tangents. So if anyone has questions, just throw them out. If I get sidetracked, I don't mind, right? So knock yourselves out. Right, so let's start. I'm going to do this chronologically. So before the war, before Turing did his PhD, he was, along with many other mathematicians, starting to think about what does it mean to be computable? What does it mean to be an algorithm? What does computation mean? And the setting that this came from somehow, around the turn of the century, you had mathematicians had discovered how to really put all of mathematics on a rigorous logical basis. And this is how we do things nowadays, but it was not how they did things a couple of centuries ago. Nowadays, when you do a maths class, you have precise definitions. You have rigorous logical proofs, so that the results you have is not a best guess. It's not something that could be invalidated by later evidence. It is true, because logic says so. And so there was this push in the early 20th century to put all of mathematics on this solid logical foundation. And in that setting, somehow you want to, like, ideally, right, and this was one of the problems that David Hilbert put up on this famous list of problems in the early 20th century, wouldn't it be wonderful if you could have some mechanical device where you could give it a mathematical statement, turn the handle, and the device says, yes, it's true, or no, it's false. And if you could do that, you wouldn't need mathematicians, right? So that was a goal. That was a lofty, idealistic goal of mathematics. It turns out, spoiler, you can't do it, right? You can logically prove that you can't logically prove everything that you want to. And we'll come to that. But in the meantime, people needed to think about what it meant to be an algorithmic, mechanical procedure. So let's think about what's actually on the slide, which is, what is computation? Again, remember that this is all happening before they had computers. So something in the 1930s that you might think of as computation is, for instance, long division. This is my own attempt at long division with a pen, and it's probably the first time I've done this in 30 years, and I checked the answer and I've got it right, but this is a mechanical procedure that we learned in primary school. Do you promise me you still learn long division in primary school? Okay, good, for you. So it's a totally mechanical procedure. You put in some numbers, you follow the rules, you make a table, turn the handle, and the answer comes out. You could train your favorite zoo animal to do it, right? If they understood the instructions. You can certainly, in the year 2025, program a computer to do it. So this is a procedure which is mechanical. Something that is maybe less mechanical. I give you a knot. So this is a knot. It's a loop of string. There's no loose ends. It's a closed loop of string, no loose ends. what you would like to do is take this knot and untangle it so it's just a loop. It's just a loop with no crossings at all. You're allowed to assume that the string is as flexible as you like, as stretchy as you like, as thin as you like. Just the rules are you cannot cut the string. You can't cut and glue. So either you can do it or you can't. It's a perfectly well-defined problem. The answer is there's a well-defined answer, which is yes or no. It is not at all clear how to do this. I sat on a train, because this is what I do for my day job. I sat on a train once next to someone who it was a 4-hour train ride, and after 2 hours, it turned out that he was in the US military. We were in Korea, and he was on the way to some military base, and I was on the way to some maths conferences, and he said, what do you do? And I said, I untangle knots. And then for 2 hours, he talked about parachutes. But his thing was, parachutes are really easy to untangle, right? It's a mess, you just and it's done, and I know how to do it. And the way he knew how to do it was he took his parachute, he fiddled with it until it came apart. And if he couldn't do it, then the answer was no. This is not, I mean, it works for him and all power to him, right? But it's not a mechanical procedure. If you fiddle with the knot and fiddle with the knot and play with the string, and you've been doing this for 5 hours, when do you give up? At what point do you say, I've tried so hard, it must be impossible? And that question turns out to be very hard to answer. There is an answer, right? But it took until about 20 years ago till we actually got a good answer to that question, which is, well, the answer is sort of, you do n-squared operations where n is the number of crossings, but it was a big result at the time. Without that result, you don't know when to stop, and so this is not a mechanical process. And so I think both of the things I've described, I mean, somehow the first thing is clearly mechanical, and the second thing is clearly not mechanical. But trying to pin down a definition, a precise definition of mechanical, is much, much harder. And this is like, it's like, computation is like love, right? You know it when you see it. Yeah, it's not good enough. So as mathematicians, we need something precise. And so that's what Turing was thinking about. That's what many logicians were thinking about at the time. And there's a third-year course that we do in this university, which I think many people here have taken it, and one person at least was responsible for getting it back on the books. We spend maybe half that course defining what it means to be computation. It's not an easy question. So Turing defined it using this notion of an abstract mechanical device. So the abstract device is the following. It's got a tape. It's got a tape, and this is a tape like a cassette tape, like the kind of thing that you had in the 1980s, right? So the kind of thing where you've got a spool of magnetic wire stuff, right, which holds ones and zeros, and when it all comes out, you've got to stick a pencil in and fix it all up again. If you've ever done that, congratulations, you're as old as I am. But it's a tape. There's no end. This is as long as you like. It's as long as you like. This is like the memory on a computer. This is like the RAM on your computer, right? And it's reasonable to have a computer with an infinite amount of RAM. If you run out of memory, you can always pause the program, run down to the shop, get another hard drive, plug it in, keep going. Yeah? So it's somehow infinite memory is not as awkward as it sounds. So this machine has infinite memory. But what does it do? The instruction set is finite. And it's like when you write a piece of computer code, the instruction set, you've got 1,000 lines of code. That's it. The instruction set is finite. The instruction set for Turing was basically a rule book. And so the book would do things like the following, right? If you've ever had a choose your own adventure, you've got these books where you're on page 7, and it says if you want to run towards the big spider, turn to page 13, and if you want to run away from the big spider, turn to page 18, right? You sort of flip back and forth through the book, and the plot would unfold depending on the choices you made. It's like that. It's like that. So you would have this rule book that would have things like, if I am currently pointing at a 0, then replace it with a 1 and turn to page 7 and step to the right. And then on page 7, you'll have another rule that says, if the space I'm on top of is blank, then fill it with a 0, step left, and turn to page 13. And so on every page of the book, you would basically have these instructions telling you what to do, depending on which bit of the tape you were looking at and what symbol it contained. But that book has a finite number of pages. It's a simple rule set. And you just keep going back and forth until one of the pages on the book says, okay, you're finished, stop. And then the answer to your problem will be written out on the tape. So to Turing, that was what it meant to be computation. Logicians had a very different kind of definition. Well, Turing was a logician, but the hardcore logicians had a very kind of different definition. It turns out they're the same after a lot of work. In fact, there are many different ways you can try and define computation. And in some sense, as long as your definitions are reasonable, and that is not a precise word, All of these definitions are really pinning down the same things. And there's this thing which I won't talk about, but you should Google it later on. It's called the Church-Turing thesis, which basically says this. It's possible the person who taught me that is sitting in the room right now. Anyway. In practice, we don't use a choose your own adventure book. In practice, we draw this thing with diagrams. This, I'm so sorry, is one of my own hand-drawn Turing machines, which I did a few years ago for a course I was teaching, but this is really what they look like. Every page on the book is a circle. The arrows are the instructions for what to do. You see ones and zeros and lefts and rights, and these things, you Google them and you'll find these diagrams all over the internet, right? So this is how we would actually draw one of these. And so this is how Turing defined computation. And then you run into problems, right? So one of the things that had happened around this time, I say new results, it was new to Turing because this came out in 1931 and Turing was thinking about this in the 1930s. Kurt Gödel, who was a logician, showed that basically the program that mathematicians were trying to do in showing that everything could be proven or disproven, answered true or false, is impossible. There are always going to be mathematical statements which you cannot prove correct and you cannot prove incorrect. There are always mathematical questions that you cannot answer, regardless of how powerful your logical system is. Right? I've put the statement up here in quotes, any reasonable logical system. You can pin that down precisely. It takes a couple of weeks of lecturing, but you can pin that down precisely. And then this statement somehow feels like wibbly-wobbly English, but you can pin it all down precisely as well and turn it all into arithmetic. So it's some hard work, but you can do it. So Gödel says there are things that mathematicians can never prove true or false. And here's an argument, right? I give you a sentence. The sentence is talking about itself. So the sentence says, I have no proof. That's it, right? You can, I promise you, you can encode this sentence in your favorite reasonable logical system. I promise you, trust me. So either it's true or it's false. If it's false, then it has a proof, which means it's true, which is nonsense. Therefore, it's true. Therefore, it has no proof. So here is a statement which is true, and you cannot prove it logically using whatever sensible logical system you're in. If you're curious, by the way, that quote's around reasonable. What it's really capturing is the system has to be rich enough to contain whole numbers. 0, 1, 2, 3, 4, 5, all the way up to infinity. If your system's big enough to contain the whole numbers, it's good enough for Gödel's incompleteness theorem. So, mathematics is broken somehow. This was either super fantastic or super depressing, depending on your take at the time. But Turing took that, and Turing was thinking about, okay, how does this apply to computation? So Turing, around the same time as Alonzo Church, proved a similar result. And this is one of the big results that we still talk about now in what's called computability theory, which is that there are, just like Gödel says there are mathematical problems that you can never solve, Turing and Church independently say that there are computational problems that you can never solve. In particular, here is one example, and this is the first one that they found. Here is one example. I want to write a program that does the following thing. It takes your program. You give me your favorite program. I look at it and I say it will terminate or it won't. What do I mean by terminate? By terminate, I mean the program runs, does some things, then it stops. By not terminate, I mean the program runs and it gets stuck in some sort of infinite loop, right? You've got your spinning beach ball of death and it doesn't stop. You have to switch off the computer, right? So I want to write a program that can look at your program and decide whether it's going to get stuck in an infinite loop. I cannot solve this by running your program, because if it terminates, I know it terminates, but if it doesn't terminate, when do I give up, right? When do I stop trying? When do I stop waiting and declare that the answer is no? That's a very hard question, and there's someone up there in the audience who knows much more about the answers to this than I do. So you've got to do it some other way. You've got to look at the source code. You've got to look at the actual code that is contained within the program and analyze it mathematically and somehow work out that it will run forever without actually letting it run forever. So that's what you can never do. Turing shows that there is no program that can analyze another program and decide whether it will stop. When I say Church and Turing did this independently, so Church did this using what is called lambda calculus, which is something I wish I knew a lot more about, but it somehow sort of comes much more from the world of logic. Turing did this really with these concrete constructions of abstract machines. And so, in a sense, Turing's proof is I want to say more accessible, because it's really, you get your hands dirty and build the thing, right? What ended up happening, as I understand it, my history is here and there, so take any historical statements I make with a grain of salt, but it'll do. Once Turing became aware of what Church had done, they got together, and in the end, Turing did a PhD thesis with Church, and so they went off and worked together after that. But this stuff they did independently before they'd gotten together somehow. So what does this mean in practical terms? In practical terms, it means if you're trying to debug code on paper without actually testing it, it's impossible. Right? Yeah, debugging sucks for many reasons. Has anyone here been involved in university programming competitions? Oh, yeah, okay, a couple. So this is a picture from the International Collegiate Programming Contest, which is something that runs every year. We have a team from UQ that got through to the regional finals, and they're going down to Sydney next weekend to compete, to try and get a spot in the world finals. But the way this competition works is you have teams of 3, and you have one computer, and you've got to write programs that can solve problems quickly and correctly. And so what happens, you're timed, you get points according to how quickly you submit your correct solutions. So if you write a piece of code, and you discover it doesn't work, you can't just sit there and debug all day, because somebody else could be writing a different solution and getting points for that. You're losing time. So what do? There's only one computer for 3 people. You take your code that doesn't work, you print it out, you go away, and you debug it on paper walking around the snack station while someone else uses the computer to do something different. And I was in one of these teams in the 1990s, and I did exactly that, and it does suck. But actually, it's a super useful skill to have. I think being forced to debug on paper taught me how to write correct code. So there's somehow, it's actually, Turing says it's impossible, but that doesn't mean you shouldn't try. But anyway, that's a side note. So I want to give you a sense of how Turing's proof works. And for that, I'm going to use a slightly different version of the problem, and this comes from virus testing. And anyone who's been in Math 1061 with me or 1081 with me has seen this, but here it is again. So virus testing, virus checkers also suck, right? Somehow, I mean, you need them, right? You need to detect malware, but it's really hard to detect malware. What do I mean by malware? We're mathematicians, we need precise definitions. I think for today's purposes, malware, a virus, will be some piece of software which, when you run it, modifies the operating system. What do I mean by modifies the operating system? If you're Linux, it edits the kernel. If you're in Windows, it edits the files in the system directory, which you're not supposed to touch, right? So it edits the core of the operating system, which is somehow not meant to be something that ordinary programs and ordinary users can access. So that's a virus. So what is a virus tester? Its job is to take any program, like the thing that you just downloaded from some dodgy site on the internet, take that program, look at it, and decide whether it thinks it's a virus. If it thinks it's a virus, it will quarantine it and give you a warning. If it doesn't think it's a virus, it will let you go ahead and run it. Now, a really accurate way to test whether something is a virus is to just run the piece of code and see if it modifies your operating system. And I presume I don't need to explain why this is a bad idea, right? So you don't want to test viruses by actually running them. You want to test them by analyzing them. Exactly the kind of thing that Turing says should be impossible. And indeed, there's this cute result by Dowling from 1989 that says that if you have a virus checker which gets it right 100% of the time, it's a virus. Yeah? It's, okay, I give this to my first years from time to time, and the questions you always get are, why would the virus checker want to write to the operating system? The real takeaway here is that there is no perfect virus checker, right? I mean, you can't analyze the code and test whether something is a virus unless you run it. Let me give you the proof. Okay, suppose I have a perfect virus checker, gets the result right 100% of the time. So I've got that, it's a piece of software on my hard drive. So I'm going to write a new computer program. Today I'm calling it a spooky program. What it's going to do is the following. It's going to take whatever you downloaded from the internet. It's going to run it through the virus checker because I've got the virus checker on my hard drive. So I ask the virus checker, is it a virus, yes or no? If the virus checker says, yes, it's a virus, I say, okay, and I stop. If it says, no, it's not a virus, it's safe, then I modify the operating system, right? I just write to the kernel. So that's my spooky program. It's not the sort of thing you would want to run, but I can write it, right? I can write it. It's very simple to code up, assuming I've got that virus checker already on my hard drive. So you can code it up, so it exists, spooky.exe. If you're on Windows, God help you, spooky.exe or whatever. You've got that spooky program as a piece of software on your hard drive. So you can ask it to analyze itself. You can give the spooky program as input to the spooky program. So sure, let's do it, right? See what happens. If the spooky program is not a virus, then what happens? See, this is why I brought the stick. If it's not a virus, right? If it's not a virus, what happens? The virus tester, because it's perfect, it says it's not a virus. So my spooky program modifies the operating system, which means the virus checker got it wrong. So that's no good. So it means it is a virus. It must be a virus. So, okay, so what happens when I run it? I feed it to the virus checker. The virus checker says, yes, it's a virus. And I say, oop, and I stop. But we know it's a virus. It must have written to the operating system. There is only one path in this flow where it could possibly have written anything to the operating system, and that's the part that we don't have control over, which is the virus tester. So the only way for this to be correct is if the virus tester itself wrote to the operating system. So the virus tester is a virus. So that's it. That's the argument. It's very simple. It just involves taking this core idea, negating it, and feeding it back into itself. The same thing that we did with Gödel's incompleteness theorem. And that's the same trick that Turing uses to show that the halting problem is undecidable. Has no solution. Right? Same sort of trick, a little bit more work, same sort of trick. But these are, I mean, there are other things that you can't compute that you may want to do. I want to call out another queer mathematician who I thought was going to be in a different country, and it turns out they're sitting in the audience. So this is Ainsley Ainsley, that's your Instagram, Ainsley May. Ainsley did honours here years and years ago, 2017 maybe, or 18, 19, before COVID, in the before times. And Ainsley was looking at busy beaver numbers. So busy beaver numbers, the idea is the following. A Turing machine, one of these abstract machines, it's just an instruction book, right? It's just an instruction book. If it says 0, turn to page 7, step left, write 1. So the busy beaver number for n equals 2, right? For n equals 2, what you do is you take every possible book with 2 pages. Some of those machines, if you let them run, they will never stop. But the rest of them will eventually stop. So how long does the slowest machine take before it stops? Ignore the ones that loop forever. They'll never stop. But the ones that do stop, pick the longest running machine and see how many steps it took. Turns out the answer is 6. For n equals 3, the answer is 21. N equals 4, so this is nice. This is civil. That got a bit wild. We don't know the answer for n equals 6, but we do know that it is bigger than this expression. What is that double up arrow? If I have a single double up arrow, 2 arrow arrow 5 means 2 to the 2 to the 2 to the 2 to the 2. So here we've got 2 to the 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 2. That's an enormous number. Now I've got another double arrow. So I take a new tower with that many 2s. That's inconceivably large. Now I take a new tower with that many 2s, right? And we don't know that that's the answer. We know the answer is bigger than that. So somehow this escalates quickly, yeah? We will never know all of the busy beaver numbers. We will never know all of them, because if you knew every busy beaver number, you could solve the halting problem. If you know that your program that you're trying to say, does it halt or does it not, if it's got 10 pages, you just wait until you've hit the busy beaver number for 10, and then you say, I give up, I stop, it doesn't terminate. So if you could compute all of these numbers, logic breaks. So at some point, this table becomes empty. At some point, we can't even know the answers to these. And there is actually a concrete point where this happens. And this is what Ainsley was looking at for their thesis. So there's a result from 2016 that says, certainly, we don't know the busy beaver number for 7918. It turns out that since then, that number's gotten smaller. It's a 3-digit number, I believe, but they suspect it's a 2-digit two-digit number. So this is the kind of work that logicians are working on nowadays that follows directly from the work that Turing was doing back in the 1930s. I've talked a lot about computability, so I'm going to pause. Are there any questions before I maybe take a breath? Yeah.
How specifically did the number 7918 get chosen?
7918. So there's two answers. The first answer is the person who should be answering this question is 4 rows behind you. The second answer is basically my understanding is that they took a statement which you know that you cannot prove either true or false. They built a machine that looks for a proof of that statement and terminates when it finds it. So you know that, like, you'll never know whether that machine terminates, because if it terminates, the answer is true, and if it doesn't terminate, the answer is false. So you can never know whether or not it terminates. And then they basically sort of compiled that into a Turing machine using in a fairly compact kind of way. Is that Ainsley, is that a fair? Okay, Ainsley nods, I maybe learned something. So Ainsley taught me everything I know about busy beaver numbers. So, yeah, any other questions? Okay. Okay, so look, let me pause for a bit. I was mentioning that Turing is like an academic hero of mine, so it's probably the academic hero of mine. So I figured I would go on a small hunt to find some connections. The first one, yeah, I mean, it's sort of, yeah, this is like the self-serving part of the talk. The first one was the Math Genealogy Project. So there's this fabulous website where you've got a family tree of PhD supervisors. And you can sort of follow as far back as you like to see who is in your academic ancestry. And you can really go down rabbit holes with this thing. I think I'd go back to Kepler, maybe, I'm not sure. But I wanted to see how close I was to Turing, and the answer is depressingly far away. So the second entry near the top on the left is Leibniz. There's a couple of Leibnizes in this list, I think. But that's the Leibniz who invented calculus along with Newton. So you've got to go a fair way back, right? That's probably in the 1600s. Okay, so maybe that's not much of a connection. Turing was a fantastic runner, right? So Matt already mentioned front runners. I think you didn't know I had a picture up there. So this is, the running group that Matt was talking about is Brisbane Frontrunners, which is an LGBTIQ running group, which meets twice a week, and there's a handful of them there. Right? There's some there, and there's one there, and there's possibly more. So this is a picture they have these in different cities all around the world. This is Singapore, Brisbane, New York, Perth, Singapore, and Singapore. But anyway, the night that was taken, I ran, I think, 7 kilometers, and I looked completely broken compared to everyone else in that photo. Turing was a marathon Olympic style runner, right? Turing was, in many aspects, but also the running, much better than me, which by transitivity means also faster than Matt, I guess. Anyway, let's not talk about running. Let's move on. Turing was also interested in information security and cryptography, and we're coming up to the Enigma machine. Yeah, this is something I worked in a long time ago before I came to UQ. I worked in information security down at RMIT University in Melbourne, and what I was looking at there was passwords. And the thing with passwords, right? Like, there's a major problem with passwords, which is that either they're so complex that you can't remember them, or they're so simple that you can guess them, right? And neither of these things are ideal. If you can't remember them, like, you'd have this situation where people would put them on sticky notes and attach them to their computer, which is a bad idea. Or they would email it to someone and say, your password for this system. Like, who's got an email that has a password in plain text? Like, don't do it, right? Don't do it. Because anyone can read your emails as they go past. The email goes through 40 different machines between you and me. Anyway, this is an XKCD comic which points out that to make a properly secure password, what you don't do is stick a digit, a number, a punctuation key, and something else that requires you to change the keyboard setting in order to type. All you have to do is realize that suppose there's 10,000 English words that you know, right? Then if you put 2 English words next to each other, there's, what's that, 10 to the power of 8, which is 100 million. If you have 3 English words, it's 10 to the power of 12, which is 1 trillion. And 4 English words, it's like 10 to the power of 16, whatever that is, right? So just take 4 simple English words, one after another. That's not guessable at all by any remote modern hardware. And this is the point of the comic. So the password that they put up here is correct horse battery staple. And I first saw this comic, I don't know, years ago, and I still, like, if ever I try and find that comic, the thing I Google is correct horse battery staple, because I still remember it, yes.
Please don't use correct horse battery staple as your password, because it is in this
Okay, that is an excellent point. Correct horse battery staple is a bad password to use. Any other 4 words, perfectly fine. Okay, yes. So we have a cryptographer in the room. All right. So let's talk about the Enigma. So this is the machine that the Germans were using, not just during World War II, but before World War II. They were using it from the early 1930s onwards. They had commercial versions. They had military versions. I say the Enigma, but it was really somehow. I mean, they were. Like it evolved, right? Somehow it got more and more complex. The military one was bigger and badder than the commercial one. The military one in 1945 was bigger and badder than the military one in 1939 and so on. But of course, intelligence in warfare is vital. And in particular, what they were more than anything else struggling with during the war was the sinking of ships in the Atlantic. And they couldn't read the signals that the Navy was sending, so they didn't know where the U-boats were, so they didn't know where to avoid, right? So it was imperative that they could read the messages that were being sent by the German Navy. And so I'm going to talk through some of the work as to how this was cracked. First, I should show you what the machine does. So it's a box. I saw one of these. So I was at a conference once in the NSA, the National Security Agency. This is the US government cryptography agency. They were trying to recruit, so they had a booth, and they had an actual working Enigma at the booth, and you could go and press the buttons and watch the glow lamps light up, and it was amazing. So it's basically, it looks like a typewriter. There's a keyboard and there's lights, yeah? And you press a button on the keyboard, like X, and the light lights up like J, right? And that's how you encrypt. You press the message in English or German, and it lights up whatever you're actually going to send, which is the encrypted message. The mechanism was as follows. So those arrows are basically following an electrical signal. So the first thing that would happen, you would press the button, the signal will go through a plug board. You can't see it here in this picture, but you've got a copy of it down here. So this was just some wires that would randomly connect pairs of letters. I think up to 6 pairs of letters in the early versions of the Enigma. And it would just swap those pairs of letters. So it's just swapping X with a J and a P with a Z and an E with a T. Yeah? That was part of the cryptographic key. So where those wires were, which letters you were swapping, you didn't know if you were trying to intercept the messages. So it goes through this plug board, then it goes through these 3 rotors. The rotors had 2 copies of the alphabet, so the inputs and the outputs. So 26 inputs, 26 outputs, and they were wired together in some unusual ad hoc way. This was fixed. This was a piece of the hardware, right? So you didn't change the wiring. The wiring, that was immovable. That was baked into the actual device. The Allies didn't know the wiring. They couldn't build one of these things. They didn't get their hands on one. But what the wiring did is it would basically permute the alphabet. So it's like one of these ciphers where an A becomes a Q and a B becomes a T and a C becomes an X and whatever. Just a translation table. But the key thing is that every time you pressed a button, the wheel would move. The rightmost wheel would move. You press the next button, it moves again. You press the next button, it moves again. And what this means is the cipher is changing with every single key press. So every single letter in the message is encrypted with a different code. The different code, because the wheels are moving. And it's like a clock. So once that first wheel hits 0, the second wheel moves once. And then, like the minute hand on a clock. And then eventually, after 26 times 26 rotations, the cog on the right will move, right? And so, sort of, the further left you went, the more slow moving it went. Later versions of the Enigma had 4 cogs and then 5 cogs. Then it would hit this reversing drum, which had the whole alphabet listed out, and it would just pair off letters. So all 26 letters were arranged into 13 pairs and just wired back and forth. And then you do the same thing in reverse, and you light up a letter in return. So that's the mechanism. That's what the electrical current was doing. How secure is it? There are 26 positions for each rotor. The cryptographic key, right, the secret when you send the message is the way you've plugged in that plug board, which letters you're pairing off, but also where you start the rotors, the initial positions of those 3 cogs. That was part of the secret. And so there are 23 cubes, 26 times 26 times 26 positions for those cogs. So that's 17,000 possible starting positions, which nowadays is trivial to enumerate with a computer, but in 1932, for instance, you didn't have a computer to enumerate them. And it was much more work to do by hand. On top of that, you've got billions of possibilities, literally, for this plug board. So somehow there's a lot of possible keys. And every letter is encrypted with a completely different cipher because the cogs turn. So this looks fabulously secure, right? The Germans were very confident. And it's a very hard problem. It was difficult to break on and off. But, okay, so what I actually want to talk about to start with is not Turing's group, but what happened before then. So this is before the war, in the early 1930s. And this was some Polish mathematicians, where somehow it was clear in the 1930s that Hitler had his eyes on Poland. They had an interest in trying to understand what was going on and reading transmissions, and they knew that this kind of machine was in use. So they needed to be able to crack it. They needed to be able to crack it. And so the Polish government put together this group of mathematicians, and in the end there were 3 mathematicians sort of at the core. I guess the lead of them was Marian Rejewski, who is the one who I've pictured here. And their job was very hard because it wasn't just they were trying to crack keys, they didn't even have the hardware. So the first problem they had to solve was even building one of these machines for themselves. And when I say they didn't have the hardware, they knew that it had rotors and cogs and plug boards and glow lamps, but they didn't know the wiring in the rotors. So they couldn't wire up the rotors, you know, that random rearrangement that gets turned around and around. And if you don't have the wiring, you can't build the rotors and you can't even, where do you start, right? So they did it. They reverse engineered the hardware, and the mathematics that they used to do this is amazing. And the cracking of the Enigma, I'll come back to that. So the cracking of the Enigma is somehow, people describe it as the greatest tour de force of mathematical cryptanalysis that we will ever see. Cryptanalysis is the breaking of codes. And that's because somehow the codes were big enough to be interesting mathematically, but nowadays codes are somehow too good, right? They're too hard to break. Then the codes were very hard to break, and the mathematics they used to break them was amazing. Turing's group developed what became a computer. Rejewski's group used abstract algebra to reverse engineer hardware, which is somehow, which has never been seen before. So let me sketch some of what the Poles did. First, some observations. Because this reversing drum pairs off letters, what it means is, if you go forwards and then come out, if you go backwards, you'll come back to where you started, right? Because the letters are just being paired off. So the forward process and the backward process are the same, which means that encryption is the same as decryption, which is extremely convenient if you just have, so you just need one device, an Enigma machine, which can both encrypt and decrypt. So if X encrypts to Y, then you know that Y encrypts to X. Encryption and decryption are the same, and that's because of this reversing drum at the end. The second thing you can observe, also because of this reversing drum, is that when you go forwards through this machine, you will, when you hit the reversing drum, jump to a different letter and take a different path out, which means that the letter will always change. The letter X will never encrypt to X. Right? Encryption will always change the letter. And that's a small but important observation. But it goes beyond that. There were also issues in the way that the Germans were, at least early on, operating the machines. And so the operation procedure was the following. You had a daily key, which everybody had in a book. The key is a 3-letter setting for these cogs, right? The 3 positions of the rotors. And you need that daily key because everyone needs to be at the same starting point so you can send messages to each other. So you've got a book that says, for January 7th, 1931, the daily key is BAD, bad, yeah? And so anyone who wants to send a message starts by setting the machine at bad. Now it is bad, that was not intended, it is not a good idea to have lots of data all transmitted using the same key. Modern cryptographers know that, but the Germans knew that as well back in the 1940s, 1930s. And so what would happen is the following. If you want to send a message, you pick your own random key. So I'm going to pick cat, right? I set my machine to the daily key, which is bad, and I encrypt my own random key, cat. So I set the machine to bad, and then I type CAT. But then, just to be sure, I do it again, CAT. So I send cat. And then I start again, I reset the machine. This time the initial position is CAT, my own unique key, and then I send the real message. So that's how they were using it. And the foot in the door to breaking the cipher was the fact that you knew those 6 letters that were sent with the daily key was the same 3 letters repeated once. So what you knew is that the first letter is the 4th, the second letter is the 5th, and the third letter is the 6th. So what can you do with that? So suppose we've got the enigma, we see the ciphertext IYKWIM. By the ciphertext, I mean the encrypted message that comes through the air, right? What is it? IYKWIM. So I see that, and I want to learn something about what the actual wiring looks like. I don't know that the secret message key is cat cat. I'm the Polish now, right? I'm trying to break this system. So I don't know that it's cat cat. But what I do know is that encryption is the same as decryption. So whatever cipher is being used for the first letter works both ways. And whatever cipher is being used for the 4th letter works both ways. Which means if I start with the I, and then I use the cipher that comes from the 1st position, and then I use the cipher that comes from the 4th position, I'm going to go up to a C, which is the same as that letter, and down to a W. So I don't know the 1st or the 4th cipher, but I do know that if I do them one after another, I will turn I into W. Likewise for the 2nd and 5th, likewise for the 3rd and the 6th. What happens then? All of these 6 letters, and only these 6 letters, are using the daily key, which means everybody on that same day is using that same 6 ciphers, A, B, C, D, E, and F, only for those first 6 letters. So I just sit and listen to transmissions all day, which were all using the same daily key, which means eventually I can recover completely the cipher A followed by D, and the cipher B followed by E, and the cipher C followed by F. So now I have 3 complete descriptions of these product composite ciphers, AD, BE, and CF. That's a start. That's a start, right? And then you can keep going. You can use other tricks. Sometimes the operators would be lazy and they would pick a daily key. Instead of cat, they would say GGG. Right? They would just hit the same letter 3 times in a row. That's the 1930s equivalent of having a password 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? But they would do it. And so the Poles would hope to see that. If the daily key looked like that, there were some more equations you could cook up. And eventually, you work your way to actually being able to break it open and determine exactly the wiring of those rotors. And they built the machine. They built the wiring without ever clapping eyes on a real functioning enigma, which is amazing, right? I meant to stop, but I do want to say something more about Turing, because what happened was, right before Germany invaded Poland, they could see it coming, right? So they basically, the Poles, it was no longer viable for them to keep what they were doing in Poland. They gave what they'd done to the French and the British, and then eventually the work was all continuing up at Bletchley Park, which is where Turing was working. And at that point, it was the opposite problem. They had the hardware, but they needed the keys. They needed to crack the keys. And for this, they built what is called the cryptological bombs. And this is some of the cryptographic work that Turing is most famous for. And these were essentially machines that were doing logical deductions, like a modern computer, but a precursor to a modern computer. They were essentially trying to do a brute force through possible rotor settings. They knew, right? They used what they knew. First of all, they had to guess at what the real message might be. If you watch the film with Benedict Cumberbatch, they say maybe the message is going to end in Heil Hitler. So they say, okay, suppose these letters in the ciphertext correspond to Heil Hitler. And that's some information that you can guess at as a starting point. That's a very powerful kind of attack. It's called a known plaintext attack, and it's something that cryptographers talk about all the time today. They used the fact that X cannot encrypt to X. If they ever tried something where X encrypted to X, that was a contradiction, and it moved on to the next step. And essentially, this machine would work its way through different combinations of rotor settings until it found something that didn't break any of the known facts about the enigma, that matched the piece of plaintext they were guessing, that never encrypted a letter to itself. And when it did that, somehow the wiring through the machine would be blocked. And the machine would stop, and someone would look at the settings, write them down, and give it to the humans to keep going. Then they would set the machine going again and try more and more possibilities until it stopped, which then they'd give it to the cryptographers and so on. So it's basically these machines were taking an enormous brute force search and stripping it down to a handful of potential useful keys. And that was enough for them to be able to read a ton of a ton of actual military data during World War II. The argument is that it's hard to measure what could have happened without it, but the typical thing that people like to say is that this would have shortened the war by a couple of years and saved countless lives. If you ever want to try your hand at this, GCHQ, Turing was working at the government Code and Cipher School, GC and CS, that after the war became GCHQ, which is the British version of the NSA. This is the British Cryptographic Agency, stands for the Government Communications Headquarters, I think. So they put out a Christmas card every year, which has got some cute little puzzles for you to try. And so go Google the GCHQ Christmas cards and have a play. I will say, can I take 3 more minutes? Okay, Matt says I can have 3 more minutes. I do want to mention the Turing Test, because this is somehow what we're meant to be talking about today. The Turing Test, so this was after the war, right? So this is sort of less mathematics and it's more philosophy in a sense. This is about artificial intelligence. By the 1950s, they have machines, and people start asking questions like, can machines think? Can computers think? As a mathematician, you shudder, because, okay, now we know what a computer is. They solved that problem in the 1930s. But what does it mean to think? This is a fabulously vague word, right? And you can argue about it for hours because you don't have a precise definition. So the Turing test is basically Turing trying to pin down what it means for a computer to think. And the test, if you haven't seen it before, is the following. Umit, if you're there, so that's my husband in the 4th row. You have to guess who these pictures were modeled on using the AI generator. So the idea is there's a wall and there's 2 parties communicating in sort of unseen. No physical interaction, just text messages. One of them is a human, one of them is a computer. And you, the interrogator, are having conversations with both of them, and you have to decide which is the human and which is the machine. And if the machine can fool you into thinking it's a human, then Turing says, let's call that the machine is thinking. They're exhibiting the behavior that you would expect of something that thinks, so let's define that to be what it means to think. It's a definition. This is a definition problem that he's trying to solve. Because once we agree on a definition, then we can argue about what's true and what's false, and what's right and what's wrong. By the way, you do this all the time, yeah? I hate these things. You do these all the time. These are Turing tests, which are also trying to tell computers and humans apart. I won't say any more about that. I've spent enough time in my life on those things. But this is the Turing test. You do them all the time. Turing's answer to this was, sure, right? Give it 50 years, a gig of RAM, sure, computers can pass the Turing test. And he then gives a raft of arguments as to why the answer should be no, computers can't think. And then he strikes off each of these arguments. By the way, download the paper. It's very readable. It's a philosophy paper. You don't need to know anything hardcore to understand it. ESP shows up as one of the reasons. Apparently they were taking ESP very seriously in the 1950s. And then he says, well, but how will we actually know? Just wait 50 years and then actually try it. And by the way, 50 years, the clock's run out on that. Nowadays, yeah, sure, computers can pass the Turing test. I've interacted with service agents for airlines or hotels or whatever, and I have no idea whether I'm talking to a human who's very busy or a machine that's using AI to try and answer my questions. I genuinely, sometimes I don't know. So I claim this is solved. I think many people would agree that the Turing test is passed. So the real question now is that the right definition? Actually trying to pin down what is the right definition is often much harder than solving the problem itself. So look, I will finish off in my last minute with just a summary of what happened to Turing after all of this work. For those of you who don't know the story, so in 1952, his house was broken into. He had a lover who he'd met, I think, the previous month, and it turns out that the burglar was acquainted with his lover. And so he reported the burglary to police, and then he just said, my lover knows the burglar. And so he outed himself to the police as gay, at which point they charged him, convicted him for gross indecency, took away his security clearance, and then said you can choose between jail or chemical castration. He chose the chemical castration. This is basically drugs that were designed to reduce his libido, but also changed his body in ways that he had not consented to. Well, he did as opposed to jail. And then 2 years after that, he died. He died of cyanide poisoning. I believe the jury is still out and possibly will forever be out as to whether it was suicide or an accident. There are arguments to say that he may have committed suicide. There are arguments to say that it was an accident because he was doing experiments in his spare room with electroplating. And I leave you to read the history books and sort of come up with your own interpretations of what happened. 2013, he got a pardon from Queen Elizabeth. The Parliament wouldn't do it. They were umming and ahhing for years, and eventually the Queen just stepped in and said, I give my royal assent of mercy, and pardoned Turing for his conviction. And then 4 years after that, there was a law, which is colloquially called the Alan Turing Law, which pardoned everybody who'd been convicted under similar offences, which are no longer offences in the year 2017 or 2025. So he was not treated well by the British government at the time, certainly, in any measure. Nowadays, he's on the £50 note. So read about Turing's history. It's very interesting. His mathematics is very